You know, when you think of geometry, you probably think of high school, right? Protractors, compasses, maybe some proofs that made your head spin. But what if I told you that there is a secret history to geometry? A 2,300-year-long story that connects the ancient Greeks, the very fabric of our universe, and yeah, the artificial intelligence that is shaping our future right now. Let's get into it.
Right, so what is the connection here? How on earth could a single idea link up ancient Greek philosophers, Albert Einstein's mind-bending view of the universe, and the AI of tomorrow? Well, the answer is geometry. Just probably not the geometry you remember.
So, to really understand this, we've got to go all the way back to the beginning, back to ancient Alexandria. For almost 2,000 years, one man's vision of space was the only vision anyone considered. Welcome to Euclid's perfect world.
Around 300 BCE, a mathematician named Euclid wrote a book called The Elements. Now, to call this an influential textbook, that is a massive understatement. For over 2 millennia, this book was second only to the Bible in how much it was studied. It was, without a doubt, the absolute bedrock of all mathematics.
And what made it so powerful, so revolutionary, was the method. See, Euclid didn't just list a bunch of facts. He built an entire logical universe from just a handful of starting assumptions. He called them axioms. Every single theorem, every proof, it all flowed with this perfect, undeniable logic from those first principles. This became the gold standard for how you do math, period.
And here they are, the 5 postulates, the 5 self-evident truths his entire system was built on. The first 4, they feel super obvious, right? You can draw a line between 2 points, you can extend it, you can draw a circle, all right angles are the same, check, check, check. But that 5th one, the parallel postulate, that one always felt a little different.
It's just so much more complicated than the others. For generation after generation of mathematicians, it felt less like a basic truth and more like something you should be able to prove using the other 4. It was this little itch they just couldn't scratch. This tiny little crack in what was otherwise a wall of absolute perfection.
So after literally centuries of trying and failing to fix the system by proving that 5th postulate, a few brilliant and frankly brave minds decided to try something completely wild. They asked, what if the postulate isn't just unprovable? What if it's just wrong? And look, this wasn't some quick little discovery. We are talking about a 2,000-year mathematical obsession. You had thinkers from Omar Khayyam in the 11th century all the way to Sakari and Lambert in the 18th century, all trying the same trick. Assume the postulate is false, and then wait for the whole system to contradict itself and fall apart. But here's the crazy part. The logic never broke.
And that led to this enormous mental shift, which is captured perfectly here. In the early 1800s, 3 mathematicians, Gauss, Bolyai, and Lobachevsky, all independently had the same incredible idea. Instead of trying to fix Euclid, they embraced the flaw. They decided to see what would happen if they built entire logically consistent geometries where the parallel postulate was simply not true from the get-go.
And this is what those bizarre new worlds look like. On a sphere, like the surface of the Earth, there are 0 parallel lines. Any 2 straight lines you draw, like flight paths, will eventually cross. But in this other weird satellite shape, a hyperbolic world, you can draw an infinite number of parallel lines through a single point. All of a sudden, Euclid's flat world wasn't the only game in town.
Well, this incredible breakthrough created a brand new problem. If all these different kinds of geometry were mathematically possible, which one was real? Which one actually described the universe we live in? Was space flat, like Euclid said, or was it curved? The answer came from a guy named Bernhard Riemann. He had this amazing insight that maybe our universe isn't just one single shape. Maybe its curvature could change from place to place. So he developed the mathematical toolkit to describe exactly that. Any curved space in any number of dimensions where the rules of geometry could be totally different from one point to the next. And this, it turns out, was the exact toolkit that Albert Einstein was looking for to build his theory of general relativity. He realized that in our universe, everything flows from this one thing called the metric. Just think of the metric as the local rule book for how to measure distance. Once you have that rule book, you can figure out the straightest possible path something can take. And once you know those paths, you reveal the overall curvature of space-time, which is what we actually feel as gravity. This quote really nails just how huge of a change this was. Physics wasn't about objects moving around on some fixed, boring Euclidean stage anymore.
Now matter and energy were telling spacetime how to curve, and in turn, the curvature of spacetime was telling matter how to move. The stage itself had become part of the play.
But all this creativity left things, well, a bit messy. By the late 1800s, mathematicians had this whole zoo of different geometries: Euclidean, hyperbolic, spherical, you name it, and nobody had a clue how they all related to each other. They desperately needed some kind of unifying principle.
The solution arrived in 1872 from a young German mathematician named Felix Klein. He published this research proposal, which everyone started calling the Erlangen program, and it completely changed what it meant to even do geometry. Klein's idea was just beautiful. He said, everybody, stop focusing on the shapes and start focusing on the symmetries. In other words, what stays the same when you move something around? For instance, if you slide a triangle across a flat table, its angles and side lengths don't change. That, right there, is Euclidean geometry. It's the study of things that are invariant to sliding and rotating. Klein realized that every single geometry was just the study of what properties stay the same under a different set of rules. It was simple, it was powerful, and it unified the entire field overnight.
Okay, so why does a 150-year-old idea from Germany matter to you today? Because, and this is the incredible part, we are seeing this exact same story, this zoo of ideas that needs a unifying principle playing out right now in the world of artificial intelligence.
Seriously, the world of deep learning today looks a heck of a lot like geometry did back in the 1870s. We've got a whole zoo of different AI models: CNNs for pictures, transformers for language, GNNs for networks, and they're all kind of doing their own thing, with no real deep principle connecting them.
And so, what are researchers doing? They're going straight back to Felix Klein. This brand new field called geometric deep learning is trying to do for AI exactly what Klein did for geometry: build a single, unified framework based on these fundamental ideas of symmetry and invariance. This blueprint basically shows the core idea. Instead of building a totally new AI for every single problem, you build one that respects the natural symmetries of the data itself. Think about it. A picture of a cat is still a picture of a cat if you turn it upside down, right? So your AI should be built with that rotational symmetry baked right in. A social network doesn't change if you just reorder the list of users. By building these principles of symmetry directly into the AI's architecture, we can make models that aren't just more elegant, they're smarter, way more efficient, and a lot more reliable. So we've gone from Euclid's perfect, simple lines to the curved reality of our own universe, all the way to the fundamental structure of modern AI. It just goes to show you, geometry was never really just about shapes. It's about the deep underlying symmetries that govern reality. It really makes you wonder, what's the next great zoo of ideas that a geometric perspective is going to come along and finally tame?